Thank you very much. Good evening, everybody. I'm going to today talk through Starling Bank and its architecture, and I'm going to give you a bit of background and insight into the sort of the forces and the ideas that we were grappling with in IT and in banking, and I'm going to talk about how that led us to make some of the architectural decisions made and how we ended up with the architecture that we did. So I'll also give you, those of you who haven't, who's heard of Starling Bank here? I like that that number goes up every time I ask it, so that's good. But for those of you who haven't, I will give you an introduction. All right, so let me start off with giving you a bit of a background into the problems that there are in banking with respect to IT, because that informs a lot of where our data architecture decision making comes from. So we'll start with this quote from Mark Zuckerberg, which sums up which was for a time Facebook's unofficial motto, and I think sums up the spirit with which tech startups normally behave. This idea that you've got to start deploying code fast, quick, get it out there. It's not about deploying code that's rubbish. It's not about deliberately trying to deploy bugs. It's about understanding that sometimes you have to sacrifice 100% absolute accuracy quality in order to get stuff out in front of the customer fast, in order to get code out there so that your customers can interact with it and so that you can see what they're doing with it. Because it isn't really giving you feedback. You aren't really getting an understanding of what your code does until you put it out in front of a customer and the customer starts using it. So this epitomized the sort of tech startup culture. It epitomized the sort of philosophies that Facebook, Google, Amazon, Apple, and so on were dealing with. However, banking said no. Yeah, banking said, no, that's not for us. This is a quote from Harry Potter, and I think it sums up what people want to think of when they think of banks. Now, the biggest commodity banks have, the biggest thing that they have to have is not actually money, but it's trust. Banks have to have trust. That's their biggest asset. If people don't have trust in their bank, what happens is they all queue up outside the bank and try and withdraw all their money, and the bank collapses. Because no bank has enough money to pay back everyone who's deposited money at the bank, because they've lent it out if they're going to make some money for it. So if everyone tries to withdraw their money simultaneously, the bank collapses, as happened to Northern Rock back in 2007. So this idea that actually, banks need trust is a very big thing with banking. And that sort of inherent conservatism of in banking, that inherent, we've got to make sure that we keep our customers' trust. We have to make sure that our code is very secure, our code is very reliable. It started to leak into their IT practices. So the IT departments of banks tended to be very, let's keep it slow, let's make sure that we check our deployments all the time, let's make sure that we don't release code too fast, let's make sure that everything is very, very reliable and so on. So they tended to release code to production once every 3 months or so, if that, and even that was seen as a bit, ooh, that's a bit, you're going a bit too fast there, slow down, cowboy. You don't want to, break anything. So this was this sort of inherent conservatism in banks and how banks deployed and how banks designed their architecture to be. Everything was very, we've taken our server, we've put it in a safe room that is locked in the building of the bank so that no one can actually even physically get at the server. It was all very, the server is the new, what we keep in the vault vault. Instead of keeping gold bars in the vault, we now keep our server in the vault behind a locked door with 3 keys to get access to it, and so on and so on. However, so banks are adopting this very safe, we don't move fast, we don't break things, and so on. Now, this might mean they go very slow when it comes to IT, but at least it means that they never suffer an IT problem. Some of you are awake and caught that as a joke. Let's go into a story of a banking disaster. So, back in 2012, there was a major high street bank which was doing a code release. And they had decided, we'll do this code release. And they were releasing a change to a batch job scheduler. And this batch job scheduler is something that basically it runs every night and schedules a load of jobs that need to be run every day at the end of every day to add up and do some calculations for transactions that have happened across the day. And they had sign-off for the code change. They had tested the code change. They had made sure that they had got a rollback plan in case the code change went wrong, and so on and so on. So they had all of this in place, and they released the code change into production, and they monitored it. And it, they weren't sure. It didn't look very good. It was a bit iffy. They were seeing some performance degradation over what they had before. So the next day they sat round and they said, well, I guess we'll roll back, right? We'll roll back what we've deployed. So the next evening they performed their rollback procedure. And then all hell broke loose. Because it turns out that while their rollback procedure worked fine for the code, they hadn't really taken into account the database changes, and they didn't roll back correctly. What happened then is that the code at the previous version was running over the database for the next version, and the two didn't interact very well. But the batch job scheduler didn't know about that and didn't care, and so scheduled a job. That job completely failed, but it didn't care. It went on and scheduled the next job. But it turned out that job 2 needed job 1 to complete successfully. And if job 1 didn't complete successfully, then job 2 just produced complete nonsense and garbage. But they didn't notice this, and this system just started going on and was producing garbage, and it was mucking up everyone's balances, it was mucking up mortgage calculations, it was destroying, transaction lists, not sending out payments correctly. It was doing all sorts of crazy things that were completely destroying the system. This meant that everyone's mortgages, bank accounts, current account balances, payments, etc., were all completely jumbled up. And the bank took almost a month to correct everyone's money back to where it was. And obviously, this causes a massive dent in their trust. If for a month people are going, well, I don't know what my balance is, that's horrendous for a bank. So the key lesson here is that you can move fast and break things, or you can move slow and break things. If you develop, you break things. And this is a key insight, key thing that you have to acknowledge when you are going into banking, where reliability, security, trust are at a premium, and you have to have them in financial services. You have to acknowledge that at some point something is going to go wrong and you are going to break something. And you have to take that idea and you have to put it into your architecture. Before I go on, just for those who haven't heard of Starling Bank, I'm just going to briefly introduce who we are. We like to describe ourselves as a tech startup with a banking license. We are a cloud-based, mobile-only bank. So you, in order to apply for a bank account, you download the app onto your phone. You apply for a bank account entirely through your phone, and then you do all your banking using your mobile. We offer all the standard features you'd expect from a bank account, a debit card, direct debits, faster payments, and so on, as well as other features that we think are new and innovative, things like aggregated spending data or fine-grained card control so that you can switch your card on for ATM withdrawals but off for contactless payments, for example, or vice versa. We have all of this, and we're constantly developing and deploying new features, new account types. We've recently launched Euro accounts so that you can denominate your money in euros as well as in pounds, and so on and so on. And we built all of this in a year. I mean, that's a bit of an exaggeration. It was more like a year and a half. But we started off in early 2016 building a bank, building the actual code behind the bank. And then in 2017, May 2017, in fact, May the 9th, 2017, so exactly 2 years ago today, we launched the bank into the App Store. And then, 10 months later, March 2018, we were declared the best British bank at the British Bank Awards. And that we re-won that award this year, so Best British Bank 2 years running. So we went from having no bank to having a bank in half a year, and then 10 months later having the best bank and keeping that. So we're moving fast, we're deploying fast, we're developing very quickly. So how did we manage to develop very quickly while still having that sort of trust, reliable, secure setup that customers require? So this is where I want to get into the software architecture, because this is this is one of the key factors behind our success, I think, is how we've designed our architecture and the principles behind it. So I now want to go in and talk about that. So the first question you have to ask with architecture is, the monolith as an idea, as a concept, has been sort of dismissed as people have moved on to microservices and have said, microservices is the way to go. Let's do a microservice-based architecture. Before we rush to that, let's consider why the monolith is a problem, why designing a monolithic architecture is a problem. The problem with a monolithic architecture, mainly from a reliability point of view, is if you develop, you break things. And if you break the monolith, you break the monolith. You break the whole thing. So you can't just break a bit of the monolith, you have to break it all or none of it. And this is a problem for reliability. You're going to break things, and you want to, when things do break, you want to give the customers the best possible experience despite the break that you can. So ideally, you'd want a little bit of your architecture to fail, not the whole thing. So this is the main problem from a banking perspective with a monolithic architecture. So we've dismissed that and we've moved on to non-monolithic architectures. However, let's go on to the distributed architecture. So we've distributed our architecture, and we've got our architecture in lots of different systems, microservices all over the place. But as we saw earlier with our rogue batch job scheduler, the problem with distributed architectures is if you get a bug or a problem appearing in one, that can quickly spread to another. The reason being that, the first system, System A, says, right, I'd like you now to calculate these mortgage payments, and if the balances aren't correct on that, on the customer's accounts, those mortgage payments might be calculated incorrectly. But if the second system doesn't care about that or doesn't know that the balances are incorrect, it might just merrily go along and calculate the balances anyway, and now your problem has spread from one system to another, and then another, and then another. And you can have your bug starting in one part of the application, spreading very quickly to other parts of the application as well. So the question is, how do you prevent this? How do you prevent this rapid wildfire spread in these days of microservices where you have 800, 900 different services running all over the place? How do you prevent the spread of problems from one system to another system to another system, like a virus, essentially, across all of your systems? So Let me talk about how Starling Bank approached this, designing this problem, designing an architecture to be reliable. We've designed things off the back of an architecture called self-contained systems. And if you go to the website there, you can read more about self-contained systems. We haven't adopted the principles here in their entirety, but we've taken a lot of our ideas from them. So what self-contained systems are is, rather than having microservices, we have what I call microliths. So we have about 20 to 30 different services, each of which are designed to work in a specific business area. So, for example, let's say card processing, or payment processing, for example, or dealing with direct debits. So we have all of these different services processing different areas of the business. Each of these services is running in the cloud, because we're a cloud-based bank, so they're running on AWS, in EC2 instances in the cloud, and we're running probably 2, maybe 3 instances of each of these self-contained systems in the cloud. Each of them has their own database, one database for all the instances, and each of them has their own APIs. And those APIs can be used to connect to maybe the mobile phone, maybe the management portal, which is the application we've got for the managers of the bank to run the bank with, maybe to each other, and maybe to outside systems as well. And so we've got, different API contexts, each of which have their own different levels of security, because obviously you're more trusting of things that are connecting internally than you are things that are connecting from the outside. However, crucially, I say they're more trusting, but they're not completely trusting. We don't blindly trust that when one system A contacts system B, we don't blindly trust that system A is perfectly correct in the commands it issues. Maybe it's not correct. Maybe it has misunderstood what it is doing. Maybe it is doing something insecure. Maybe it has asked for something to be done twice rather than once. So the systems are mistrustful of each other. We've built this mistrust into the code, and that's a key point, to have your systems be mistrustful of each other, because that way you can encourage reliability. The systems also don't depend on each other. So there's no startup dependencies from one to the other. They're all independent. So if one goes down, then some of the banking app or the banking functionality via the management portal will fail, but not all of it will fail. So that's another thing we can degrade gracefully. There's also no distributed transactionality across the different systems. So if a task needs to be performed, for example, and that task is a single command which I want to succeed or fail atomically, but it requires processing in multiple different systems, you have to make sure that each of the different systems will catch up if something fails halfway through. You have to anticipate that something could fail halfway through and be able to catch up. So we came up with this brilliant name for the architecture, which stands for lots of automated systems constantly trying to do idempotent things to each other, or losci additio, and it just rolls off the tongue. We decided after a while, it was pointed out that by someone from AWS, that this could be shortened to ditto architecture. So we decided that that was slightly more memorable than losci additio. So ditto architecture, do idempotent things to others. This concept of idempotency is very important for making sure that you do things reliably. Idempotency in this context means making sure that if a command, oh, I've disappeared. wire fail, there we go, means that if you do, idempotency in this context means that if you issue a command twice, the exact same command twice, that it has the same effect as if you issued the command once, or if you issued the command 3 times, 4 times, 5 times. And the reason this is key and is important is to make sure that you don't process a payment twice, for example, because that's a very quick way to lose trust. If a customer says, I'd like to send £20 here, and you go, very well, I've sent £40 there, then the customer quickly loses trust in your ability to do maths, which is very important for a bank to have the trust of its the confidence of its customers in its ability to do maths. So, some principles, key principles for Ditto architecture. Do everything at least once and at most once. At least once and at most once. So the reason you say at least once and at most once and not just once is because that covers the 2 failure modes that you have to get round. If a customer wants a payment to be made and you don't make it, that's a problem. If a customer wants a payment to be made and you make it twice, that's a problem. So those are the 2 failures you have to get around. So you have to make sure that you retry things. So the systems have to be mistrustful with each other in the sense that if system A asks system B to do something and system B doesn't give it a response, system A can't just say, oh, it probably happened. System A has to retry. It has to say, okay, I'm going to wait a little bit and then issue the command again. But system B has to be able to process that command idempotently. It can't just blindly accept commands from system A and go, okay, yes, I'll do that, yes, I'll do that, yes, I'll do that. It has to make sure that it receives the command and then says, have I already done this one? Have I processed this before? All commands thus there must be issued with a unique identifier. These unique identifiers must be perpetuated throughout the system. They must be assigned to the command, the whatever is being instructed, as soon as it gets into the system, and then must follow it throughout the system and throughout all of the different self-contained systems that it touches, to make sure that you process, in each case, each system that needs to process it, processes it only once. And if something gets asked to process something twice, one of the key factors of idempotency is that it shouldn't explode with an exception and go, oh, this is a big problem. It should just go, okay, I've processed that. Thank you very much. And, it should do nothing with it, but it should, just return 200, okay, yes, everything's fine, I'll process that for you. The system as a whole, thus, works towards eventual consistency. And it might get out of sync for a bit, but this constant retrying of commands eventually leads it towards an eventual consistency, where it has processed everything. And this is fine, that maybe something will be out of sync for a few minutes, but generally speaking, customers are okay with that, as long as eventually it, reasonably quickly catches up. No distributed transactions, as I said, mistrustful of each other, mistrustful of anything coming from outside, but also anything coming from inside. Anything that's not within the service of itself, the service is mistrustful of, to make sure that it, checks and rechecks whether it's already done something, whether something can be done, whether something should be done, whether, whatever is being asked for is permitted. So, with all of this in place, you get some, if you put all of this in place and put this throughout your services, you get some brilliant benefits. The main benefit, from which all the other benefits stem, is that instance termination is safe. So you can safely cut off an instance of one of these self-contained systems at any time. And you can just chop it and say, this is gone now, bye, disappears. Because when another instance of that self-contained service comes up and starts running, it will start picking up again where the other system left off. And if something's already been processed, then it will try and reprocess, but it will do so idempotently. And if something got missed, it will be picked up and processed through. And if something got halfway through, then it will be picked up. The first half will be processed idempotently, and the second half will be processed in the correct manner. So because this principle perpetuates everywhere throughout the systems, we can safely kill instances in the middle of what they're doing, and know that once they start up again, the system will start working its way towards eventual consistency. This means, first big benefit of this means we can deliver, we can have continuous-ish delivery. So we're not deploying every single commit into production, but we are deploying once or twice a day, maybe sometimes even up to 5 times a day. And we can get a deployment out pretty quickly. From the point of commit to the point of release, it's generally about an hour, just under an hour. So what that means is that we can deploy features, we can deploy new products and services to our customers, and fixes, if something goes wrong, very quickly. We can deploy them out at a rapid rate, which is great. It's fantastic. We have taken the once every 3 months deployment that is done at the older banks, and we have gone, no, scrap that. We're going to deploy every day. We have automated all of this. Because we do it so rapidly, we had to automate it because we need to keep an audit log. We are a bank. We need to get audited. People need to see that we are following procedures correctly. So we developed a Slack-based automatic deployment procedure, which automatically says, I'm rolling, here's what I'm committing, here are the commits that I am deploying. It goes and seeks approval. We need to get approval for releases, so it goes and seeks approval automatically. And once the buttons are clicked, it goes, great, the buttons have been clicked by people who have the authority to click the buttons. I will now release. And this is all audited within Slack. So you have an audit log of what is going on. That's fantastic. We also have this. We need to alert people to the fact that we are releasing code. We are releasing code into production. So we deployed what we call the rolling Giphy. Which is every time you do a deployment into production, you post a GIF into Slack using Giphy, which indicates some form of rolling, of which you can see various versions here. We showed this to the auditors, and they were confused. But ultimately, they said, well, you're doing what you should do, right? You're alerting everyone to the fact that code is being deployed. That's fine, that's good, that works. The auditors are continually confused by us. The first time the CIO went to the auditors, he was asked who has the keys to the server room. And he replied, not only do I not know who has the keys to the server room, I do not know where the server room is. A lot of this exercise shows that a lot of the time when people say, we would love to deploy very quickly, but regulation prevents us from doing so, we've proven them wrong. Regulation doesn't prevent you from doing so. You just have to look at the, rather than following the regulations in the way that you've always followed them, you need to look at the intent behind the regulations and make sure that you are following the intent, not just the sort of checkbox way that you have been doing it in the past. And if something goes wrong, we have monitoring everywhere. We have big monitors on the walls. We have monitors attached to the ceiling. We have monitoring everywhere that shows us what is going on at that particular time. We have alerts set up on particularly egregious things, such as if a key service just disappears or we start returning too many 500 errors to the mobile phones, for example, then we will start raising actual alarms to the on-call engineer. But we have these graphs everywhere to make sure that we can get a visual visual eye view of what is going on, and we can say, hang on, that graph doesn't look right, and then go and investigate in more detail. So it very quickly alerts us that something might have gone wrong, and if something does go wrong, we can very quickly respond and deploy another release to it. So rather than trying the rollback procedure, which is untested, untried, and will probably go wrong, we can fix forward because we can just do another release within an hour of the previous release. and we're happy to do that release during the middle of the day. In fact, the vast majority of our releases do take place during the middle of the day, and we don't have to shut the bank down and say, you know, you can't do banking for an hour because we're doing a release. We just do the release and you know, have a rolling deployment such that services are always there and up and running. And if a problem happens, then we do another release. So this allows us to get code out very quickly while still having a running bank, a reliable bank, a bank that people could feel that they can trust and use. We also test using chaos engineering, right? We can also start just having code that goes around killing our servers in production at random times of the day and night. And we can do that because we are confident that if, when something gets randomly killed, that the system will catch up and any half-completed work will be fully complete, and any, you know, commands that weren't processed will be processed because we have implemented this architecture. So, in conclusion, if you want to have a very reliable architecture, if you want to build something that has to work with financial services or, you know, something like that, something where trust is a premium and reliability is key, then you need to make sure that your services are mistrustful. You need to make sure that your architecture is designed so that you can anticipate that when things go wrong, because they will go wrong, the system can catch up. The system can say, where have I got to with this, and pick it up and process it in an idempotent fashion to make sure that all commands get processed at least once and at most once. And if you build that mistrust into your system, into your code itself, then you don't have to have as much human eye checking of what's going on, because the mistrust is the mistrust that humans would apply is there in the code. And if you do that, you can build something like a bank or a financial system at speed while still maintaining reliability. Thank you very much. Do we have time for questions? Or
If there's any questions, we have a microphone.
We have a hand went up straight away down here.
Thank you very much. Michael Pullen, I have two questions, or one and a half. It's up to you to judge. From the consumer perspective, when you do daytime release, it still takes some time. What happens with people who are getting into your bank exactly in the middle of your release?
Yep.
Some part working, some part doesn't.
So the way we do deployments is we will, for any particular service, say, what we will do is we will have 2 instances of the old version, let's call it version 1, running, and then we will deploy.
Understood.
We will deploy one of the new versions, then take out one of the old. Yeah. Switch.
And the second question about eventually consistent data.
Yeah.
You said it has to run quickly. I don't know what does mean quickly.
Yeah.
But if a user gets to your system in the middle of this inconsistent data.
Yeah. Yeah.
So how happy that user is?
Yep.
What you do about that?
So quickly from this perspective means it's quickly from a human perspective rather than a computer's perspective. So the human wants to see, if the human makes says, I'd like to make a payment, please, they'd like to see that go out, within 5 minutes, say, maybe. It depends on the human as well. Some people are happy with it going out within 5 minutes.
They expect 1 minute maximum. Maybe
I mean, generally speaking, we're instant, right? That's generally what happens. It's instantaneous. So, generally when I'm working, like when you pay with Starling Bank with your card, for example, you generally get the notification that you've spent money on your card before the terminal has come back and said accepted. So generally, and the same thing happens when you're making a payment from one bank to the other. So in 99% of cases, that's true. In 1% of cases, there is a problem, and we generally find that people are accepting of there being slight delays as long as the payment gets through.
Lucky you.
But when I say the data is eventually consistent, there is, of course, there are different parts of the app, right? There is the consumer-facing part, and there is the consumer-facing part, there is the bank-facing part. So sometimes those will get out of sync a bit. And the question is, you know, let's see how we can make it in sync. There's the other principle is that if things do get out of sync, then they always get out of sync in the customer's favor, because we have to treat the customers fairly. So if there is a problem, then the fault has to be with us, and we have to, you know, take the hit rather than the customer taking the hit. But by and large, it's consistent fairly quickly.
Hi, that was a really good talk. Thank you. Enjoyed it a lot. How do you prevent sort of very fast double spend? So if it's eventually consistent, if I launch up 2 versions of the app and maybe a human could hit the button incredibly fast, or some sort of bot could blast. How do you therefore know that person hasn't gone heavily overdrawn? Or, you know, if it's eventually consistent.
Absolutely. So there are some things that, most things in the system we do asynchronously in this eventually consistent manner. There are a few things that we have to do synchronously. One of them is checking the balance. So if you say, I'd like to spend £20, please, the first thing we have to do is take away that £20 from you. Now, this is behind the scenes. What is happening when we take away that £20 is actually there are 2 views of what money you have spent. When we take away that £20, what we do is we say what we call allocate it. That is, we ring fence that £20 and say you're not spending it, but technically and legally speaking, that £20 is still yours. But it's disappeared from your available balance. You can't spend it anymore. We've locked it around. And that locking procedure is fairly quick enough for us to do it synchronously. The rest of the process, taking it through and actually taking your £20 away from you, is a slower process which we can do asynchronously. So if you try and, you know, you've got £20 in your account and you try and spend it twice, you'll find you can't do that because it will be locked. And then the second time you come round, it'll check against the available balance and will say, well, that £20 is not available to spend because it's been locked for another purpose.
I think we've got time for one more question.
Thank you very much for that. I'd like to ask about bank is important, obviously, for monitoring capabilities. So I wanted to ask what would be the tools which you are using to identify abnormalities within monitoring. Is it CloudWatch within Amazon, or is it Splunk or in-house developed monitoring? Thank you very much.
So we use so the boards that we have, well, start again. We use Prometheus to gather metrics. Those metrics are then put out to both Grafana, which are the graphing tool that you saw on the screen there, and also to PagerDuty, which is the software we use to alert us that whether something has gone wrong or not. So those metrics are gathered. All of them are farmed out to Grafana. Some of them are farmed out to PagerDuty. You have to be careful when farming out alerts to pick out only the alerts that really are a problem, because if you farm all of the problems out to PagerDuty, then essentially the on-call engineer will just turn their phone off and throw it away, rather than having to respond to yet another minor problem. So you only really want the major problems to come through on the PagerDuty phone. So those are the main tools that we use to create monitoring.
But was the question more, how do you detect abnormalities?
How do we detect abnormalities? It depends on what system that we are monitoring. So our external systems, we just have something that checks the health of the connection between ourselves and the external systems. And if that disappears, then we immediately go, because that might mean that our cards aren't working, or you can't make a payment out from your phone, something very big. Those type of monitors are very black and white. It's either on or it's off. Other things will be much more threshold based. So errors being returned to the phones, for example, if that trips over a particular threshold, we will then raise an alert. And that threshold, what that threshold is, it depends. We have to you know, you set it too low and you raise an alarm too much, you set it too high and you don't raise an alarm when you should. So that is a subject of review and iteration.
Perfect. Well, I think that everyone could give Jason a round of applause for a brilliant talk and some very good answers to questions too.